Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated for those who are going through either differential equations or Calc 2 integral calculus, and you're working with power series or series themselves. And it is very, very common that you have within a series, a product of odd numbers, odd integers, 1, 3, 5, and so on and so forth, all the way to 2n minus 1. That happens so often that it's very nice to have a nice concise form of that rather than having to write it this way. However, I should say most individuals will end up just writing it this way, to be honest with you. However, just to let you know, that is actually equal to 2n factorial divided by 2 to the nth times n factorial. We're going to go ahead and use this video to prove that and then adjust one of the answers that I did in my class for my students. We're going to adjust that answer using this theorem. The easiest way to do this proof actually is to start on the left-hand side, even though I think a lot of people would like to start on the right-hand side, but I think the left-hand side is actually an easier way to start this proof. So let's go ahead and do that. Now I'm going to adjust this very slightly by tacking on one more term at the very end of this. And I wrote that in blue so you can see I just tacked on an extra term. So you would have to admit that that's kind of a weirdness there, but I did that for a very special reason. The next thing I'm going to do is fill in the gaps in these numbers. So it went 1 to 3, and then from 3 to 5, and then 5 to 7, and so on and so forth. What I want to do is fill in those gaps. I want 1 times and then 2, then times 3, times 4, times 5. So you can see I'm in blue, including some extra numbers that were not here originally. And you can see here that I've offset all those multiplications in the numerator by division here. So I include them in the denominator. So in reality, we still have the same 1 times 3 times 5 all the way up to 2n minus 1, because you could cancel if you wanted to these 2's, these 4's, the 6, the 2n minus 2 that's right before here, and the 2n and the 2n. So all of those can be canceled. This has not really changed the value of this fraction. Now let's go ahead and note that that numerator is actually just the product of all natural numbers all the way up to 2n. That is, it's 2n factorial. And in the denominator, it's, oddly enough, a product of the even integers, or actually even natural numbers all the way up to 2n. Now, every even number is actually divisible by 2. For example, 2 is just 1 times 2. 4 is just 2 times 2. 6 is just 3 times 2, and so on and so forth down the line. So let's go ahead and clean this up. You'll note that if you count up the number of numbers we have in this, the number of factors, I should say, in that denominator, we have 1, 2, 3, ... all the way up to n of them. We have n factors in that denominator that are multiplying. Each of them I'm going to factor a 2 out of. That is, I'm factoring out n factors of 2, or in other words, 2 to the nth, and I'll be left with 1 times 2 times 3 all the way up to n, which is just a fancy way of, or not a fancy actually, a long-winded way of writing n factorial. And if you take a look, we have now proven that the product of the odd natural numbers all the way up to 2n minus 1 is the same thing as 2n factorial over 2 to the nth times n factorial. That proof is done. QED. Now the question probably would come up like, when are you ever going to use this? And if you have worked with sequences and series, specifically if you've worked with power series long enough, you know that this product of odd natural numbers comes up all the time. It's a very, very common product. In fact, in the class that I teach, we did a Maclaurin series expansion for this function right here using the binomial series. So this ends up being x to the fourth times 49 plus x squared to the negative 1/2, because you have the square root right there. And all I did was get that 49 off of that, because I want this to be as 1 plus some number. So I divided both terms by 49. That's all I did there. And to showcase why I wanted that, well, let's go ahead and for right now, apply the negative 1/2 power on 49. So it's 1/7 because it's square root. So I pulled that out front and we end up with this guy right here. And what we're going to do with that is we are going to use this expansion, that the quantity 1 plus x to the kth power is just equal to 1 plus the summation from 1 to infinity of k choose n x to the nth. Remember, that's centered at 0 there. So I wrote the x to the fourth over 7 out front, and it ends up being 1 plus the summation from 1 to infinity. And then again, it's the power, choose n, times the argument, which normally would be called x here, but it's now x squared over 49, raised to the nth power. So far, so good. All we're doing is copying a formula, and then you would distribute this x to the fourth over 7 through to both terms. And you get to this point right here. Let me just take out my chicken scratch right there. I also cleaned up, by the way, x squared to the nth is x to the 2n, and 49 to the nth as well. 7 squared to the nth, or 7 to the 2nth. So that's where I got there. Again, I'm just rehashing an example I did in class for my students. And you should note that there is a choose notation formula, which is generally involves factorials, that you learned back in your pre-calculus course. And that formula is this one right here. I apologize that the lettering is slightly different, but you can just think of it as, I think we were writing as k choose n in the previous screen. Sorry about that it's slightly different here, but it's the same idea. N choose I is n factorial over n minus I factorial times I factorial. That formula works wonderfully if n is a natural number. However, looking at what we have, that is not a natural number. So that version is not going to work really well for us. And I'm not going to get into why. Your instructor probably should have covered that. But let's see what the alternative form is. So we're back at this screen. If n is not in a natural number, then don't use this one right here. That'd be bad news because it won't work out. Instead, you're going to use this version right here, which is basically what would happen if you were to simplify this factorial notation. So you get n times n minus 1 times n minus 2 all the way down to n minus the denominator, this I right here, plus 1 over that I factorial. And this only holds as long as I is non-zero. If I were 0, n choose 0 is defined to be 1. That's why we have a 1 in the first part of this expansion. That's the n choose 0 part. Then we start with the first term here. So now I know, okay, if I want to clean this up and get this down to this point right here and somehow magically work with this, I know it's going to be whatever this value is, which is negative 1/2, and then you're going to start losing 1 from them. So negative 1/2 minus 1, and then a negative 1/2 minus 2, and a negative 1/2 minus 3, and so on and so forth, all the way until you get down to a negative 1/2 minus this guy right here, n plus 1. And so that's exactly, I should probably have left that in there. That's exactly what I have right here. So this is where my students would see this in lecture. By the way, also you'll notice this difference here from these guys. And that's just from me taking 4 powers of x, distributing it inside to add 4 to the powers on x there. And also me taking the single power of 7 and distributing it here to add yet another power of 7 right there. So those are the explanations for that. And then I had this conversation with my students that we work with an online homework system, and generally in the online homework system, they just say write out the first 3 terms. However, I want to give you a skill here. And the skill is so that you can really reduce the complexity of this. So what I'm going to do is grab this picture right here. I'm going to move it down a little bit, and we're just going to simplify this statement. And in fact, what I'll do is I'll copy it, and there's no need for me to have moved that down. So I'm just going to copy this. And I did that because actually in my notes, I have an extra page just reserved for rewriting this answer using our previous theorem. Now, this may not look like our previous theorem, the one that we had the product of odds, but it is actually. If you look at those numerators there, that's 1, 3, 5, all the way down to something. And let's go ahead and just simplify this a little bit so that I can convince you that these are the same. So there's a little bit of explaining that I need to do here. One thing I did is I took each of these terms, or factors, sorry, in the numerator, and I pulled off a power of 2. If you think about that, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to this one. And it goes all the way actually to whatever n is at the moment. So I'm factoring out n powers of those. So this is where I get the 2 to the nth downstairs. I factored out a denominator of 2, but I did that on n of those factors. So I factored out 2 to the power n. The other thing you might be confused about is where this came from. And that just comes from me factoring off, again, that power of 2 off of that fraction. If I were to divide off a 1/2 out of that, I'd be left with a -1 minus 2n plus 2. You could double check my work there, but it is actually true that that is what that turns into. So again, we are clean up to this point right here. Now I'm going to factor a negative off of each of those factors in the numerator. So you could see there's a little bit of pre-work, and this does end up being kind of critical as you move forward. The patience to be able to sit here with a problem and work through each of the little minor details. So let's see, I'm going to factor a -1 off of the first, the second, the third, all the way up to the nth term. That is, I'm factoring off -1 to the nth. And when I do that, I'm left with just 1, 3, 5, and so on and so forth, all the way down the line until you get to this guy right here. And by the way, I didn't really bother writing it, but this is actually equal to a -2n, plus 1. If you were to factor a negative off that, that is actually a positive 2n minus 1. And that should look familiar to you. This is all over 2 to the nth, n factorial, and we still have an x to the 2n plus 4, and a 7 to the 2n plus 1. Now I say this should look familiar to you. When I say this, I mean this piece right here, because we have a theorem we just proved. The product of those first n odd numbers is going to be 2n factorial over 2 to the nth times n factorial. So that's what I'm going to replace that product of the first n odd natural numbers with. So that highlighted piece you see right there will be replaced. And you can see that I replaced that highlighted ink with this blue ink. Remember, it's 2n factorial over 2 to the nth times n factorial is what the product of odds gets exchanged for. And obviously there's just a little bit of simplification here, so let's go ahead and simplify that. All right, we get down to this, and there's not really much else you can do. I mean, there are little minor simplifications you could do here, but I like this form of it. It's not too terrible. It does look pretty terrible, honestly, but it's not too terrible. So I would call it quits right here. Now, something that my students, and I think most students would probably ask is, do you have to go from this form all the way down to this form? And the answer to that is no, not at all. This is just something that some people like to do. And I think that it's important that you keep your curiosity and you keep your mind open to different approaches to simplification. And that's just what we're doing here. We're just simplifying a statement. While we're here, let's go ahead and just use Desmos to visualize this specific summation and maybe the first few terms of it, just so that we could see what that looks like. Remember, it was supposed to be f of x equals x to the fourth of the square root of 49 plus x squared. So let's go ahead and see what that looks like in Desmos if we just expand that Taylor series centered at 0 out for a few terms. So here we are in Desmos, and I've already typed in the original function, and this is what it looks like. If you zoom out, it's not too much different than if you were to zoom in, honestly. And we're going to go ahead and type out our Taylor series expansion. It's actually a Maclaurin series expansion because it's centered at 0. But the main thing I need you to know here is that we are not going to expand out an infinite number of terms. We're only going to do a small number of terms. So let me go ahead and type them out. Now I want to stop right here just because if you're not one of my students, you may not have seen me do this before. So if you want to get a summation sign in Desmos, you just type SUM and it creates it. There you go. And remember, this summation is starting at 1, not 0. And we're going to go to, I don't want to type infinity here. So instead, I'm going to just go to 2 terms for right now. So again, the initial term here, this is actually the 0th term. And then we'll have a first and second term within the summation here. All right, I've typed out that. Let me open this up a little bit further so you can see that. And I'm going to turn off our summation right now. So in blue is the original function. And what I'm going to do is when I turn on this graph right here of g of x, it's just going to show x to the 4th over 7 plus the first and second terms of the Taylor series expansion about 0. Only 3 terms altogether. And yet when I turn that on so you can see it, it almost is identical to the original graph. In fact, it pretty much is. You can see they're the same graph for quite a while. It starts to separate. I could see it on my screen. It starts to separate a little bit out on these fringes here, but that's actually not bad. I'm going to zoom back into the center so we can play around a little bit. So what if I did not go out to the first 2 terms? What if I only summed the first term? Again, really, really good, except you can see it actually turns the corner and flips down. So remember the orange here is the graph of our Taylor series expansion about 0. And it's only the first, well, the 0th term and the next term in line, which is the first term. That's still really accurate around 0. It's the same graph around 0. Isn't that crazy? I just think that's pretty amazing. And you could talk about the error here, by the way. And I should mention as well that this g of x, a lot of people would call this, if you're summing to the first one there, they would call this, well, if you let n equal 1, that'd be x to the 2 times 1 plus 4, or x to the 6th. They would call this t sub 6 of x. That's a 6th degree Taylor polynomial expansion. And that is only because a lot of people think that you're moving out 6 terms of the series, but that's not true. You just go until you hit the 6th power, and that happens when n is equal to 1 actually. So just a heads up, you want to be very careful about that when you talk about nth degree Taylor polynomial expansions, that really your desire is to get to a, in this case, 6th degree polynomial. If I wanted to get to, for example, a let's say a 10th degree polynomial, I would need n to stop at 3, right? Because that'd be 2 times 3, which is 6 plus 4. So I'd sum up to n equals 3. And when I do that, you see the curve didn't actually change too much. It did change. It's just we can't really tell with the human eye here, but it did change. Not too bad. All right. So there we go. I hope this video was helpful. Again, really the main point of the video was the theorem to condense the product of the first n odd natural numbers down into 2n factorial over 2 to the n times n factorial. However, I wanted to add on to and showcase how to do that with a stringent example. But again, I hope that was helpful, and I hope to see you in another video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just